So now we'll see solving of first order and first degree differential equation and using the 4 different methods which we have. So let's see all the 4 methods which we have. The first method is the variable separation method. Variables separation method. And secondly, it is this is solving through variable separation method, and secondly it is solving of homogeneous differential equations. And thirdly, it is solving of non-homogeneous differential equations. And fourthly, it is solving of linear differential equations. So each of them has their own method. So this first order and first degree differential equations are solved using 4 types of methods. One is solving through variable separation method, and next is solving of homogeneous differential equations through a particular method, and next is solving of non-homogeneous differential equations using its respective method, and finally solving of linear differential equations using its own respective method. So let's see these 4 methods, starting from variable separation method. The first method is variables separation or separable method. So let's see how this method helps in solving the first order and first degree differential equation. As the heading itself says, variable separable method, it is very important we separate the 2 variables x and y in the first order first degree differential equation. So the method is about separating the variables and then solving respectively. So for example, I have the question which says solve the differential equation dy by dx equals e power x minus y plus x squared e power minus y. So I would like to solve this first order first degree differential equation in independent variable x and the dependent variable y. So in order to solve this, let me take the differential equation this modified with. Now my task out here is to take all y variables to one side and x variables to the other side. Therefore, I split all x and y variables because the method is variables separable method. I split all the variables which can be split as this using the law of index. A power m times a power n is a power m plus n. So separating this and writing this in the form x squared in this. Next, I can take e power minus y common, where I get dy by dx equals e power minus y, which is common, and I get e power x plus x squared inside. Now, all x terms I would like to take to the left and all y terms to the right. Therefore, this reduces to e power x plus x squared dx with e power y dy, because this as 1 by e power y gets cross multiplied as e power y dy. Now clearly I see that all x terms are on the left and all y terms are on the right, and hence this is separated into two variables from the given differential equation. Now once this is separated into variables, we integrate on both sides with respect to x. Integrating both sides with respect to x, we get integral of e power x plus x square dx is equal to integral e power y dy, which on splitting gives us integral e power x dx plus integral x square dx is integral e power y dy, which on further simplification gives integral e power x is by standard formula e power x, and integral x square using integral x power n by n plus 1, we get x power 2 plus 1 by 2 plus 1 equals e power y plus c, using the constant of integration plus c. Therefore, this can be written as e power x minus e power y plus x cubed by 3 equals, this is called the solution of the given differential equation. Therefore, the solution of the differential equation dy by dx equals e power x minus y plus x square e power minus y is e power x minus e power y plus x cubed by 3 equals c. C is the arbitrary constant or the constant of integration. This is how we do using the variables separation method. Now that we have discussed about variables separation method, now the biggest question which comes out here is, can variable separation method be used for any differential equation or for solving any differential equation, is the biggest question out here. So let's discuss the limitations of variables separation method. Say for example, I want to solve the differential equation dy by dx equals 2x minus 3y using variable separation method. Then I cannot solve this using the variable separation method because this particular differential equation cannot be split into all x variables and y variables aside. So this cannot be solved using variable separation method, because simply since the variables cannot be separated, into left hand side and the right hand side. Therefore, the limitations are that variable separation method can be used only for those differential equations where all x and y variables or all dependent and independent variables can be split aside. So the limitations are that variable separation method can be used for solving the differential equation only if the variables can be separated, is how we understand, and hence can be separated only then the variable separation method can be used for solving the differential equation only if the variables can be separated. Cannot separate the variables, cannot use variable separation method. Is how I understand the limitations or the learning outcome of variable separation method. Before we discuss the second method of solving the differential equation of first order and first degree, let's discuss about the concept homogeneous functions. What do we mean by homogeneous function is the biggest question in the definition. So as we know that homogeneous is something like equal in all respects, therefore equally distributed, then homogeneous function has its own mathematical definition. A function f of xy is said to be homogeneous in two variables is said to be homogeneous if I introduce the concept of k, which is equal to k power alpha of f of xy, is how I understand the homogeneous constant. So this is called, then that implies f of xy is called a homogeneous function of degree alpha in two variables x and y. So when I want to check for homogeneity of the function, I simply check for f of kx ky should be equal to k power alpha times f of xy, where alpha is a real number. Is how we understand the homogeneous function definition. So let's identify some functions to be homogeneous or non-homogeneous as related problems using the definition of testing for homogeneity. Now let's try to do this problem where the question says, is the function f of xy equals x square y plus y cube by x cube minus this. So I would like to check for homogeneity of this function. Is the function this homogeneous is the question. So let's test for homogeneity of the function. The given function clearly out here is given as f of xy equals x squared y plus y cube by x cube minus 3x y squared. Now in order to test for this function to be homogeneous, I use the test for homogeneity, where using the test for homogeneity I consider f of kx ky and then test for homogeneity. So in place of x I have kx, in place of y I have ky, which gives me on the right hand side x is replaced with kx and y is replaced with ky, and let's simplify this. So x being replaced with kx and y being replaced with ky, and similarly y cube being replaced with ky cube, and whole by, similarly with the denominator, x gets replaced with kx as whole cube minus 3 times kx and ky is what we get. Now simplifying this further, I get this as k square x square times ky plus k cube y cube whole by k cube x cube minus 3 times of k cube, k times of k square is k cube, and x y square. So therefore, I take k cube common here and I get x square y plus y cube, and again I take k cube common in the denominator, I get x cube minus 3x y square, so that this gets cancelled, and therefore I get this to be k power 0 times of f of xy, because this is the original function f of xy, that is k power 0 when I cancel. Therefore, f of kx ky is k power 0 times f of xy. Therefore, f xy given by x square y plus y cube by x cube minus 3xy square is a homogeneous function of degree 0, because it's simply 0. So the given problem, x square y plus y cube by x cube minus 3xy square is a homogeneous function of degree 0, is how I understand the homogeneity of the function connected with the test for homogeneity. Now that we have discussed about homogeneous function using test for homogeneity, the other alternative method through which we can test for homogeneity is identifying through equal powers of variables. Say for example, I have the function f of xy is x square plus 3xy plus y square. Then clearly, instead of calculating this through f of kx and ky, I can directly test for homogeneity through equal powers of variables. Now as I see that the highest power of this variable is 2 and the highest power of this variable is 1 and 1, that is 1 plus 1, which is again 2, and the highest power of this is also 2. I see that all are equal. Therefore, if we get each term with equal powers, then I can say that implies f of xy is a homogeneous function, since equal powers of 2 is how we identify. Let's take one more example and see if this is homogeneous. Now clearly I can see that each of this has unequal powers, because this has power 1 and this has power 3, and the next term has power 0 and the next term has power 2 for its variables. Therefore, this is not a homogeneous function. And I have this f of xy Now I have this problem. Let's see if this is homogeneous function. Now clearly I see that this function has various terms. By going by term, the power of this is 2 plus 4, the highest power as 6, and then the next term has the highest power as 6, and even the next term has highest power as 3 plus 3, which is 6, and the next term, which is 1 plus 5, which is 6, and 5 plus 1, which is 6, and this is 6. Now since each of the terms has equal powers, I can say that because of this equal powers, directly f of xy is a homogeneous function. But degree of the homogeneous function will be 0 because all the x and y terms get cancelled. So it's a homogeneous function of degree 0 because each term of the variables has equal powers as 6. The next concept connected with homogeneous function is homogeneous differential equation. So now that we have discussed about homogeneous function, a differential equation of first order and first degree which involves homogeneous function is called homogeneous differential equation. That is, if I take a differential equation of first order and first degree equals this. This is called homogeneous differential equation if this function is a homogeneous function, which we have discussed in the recent session. Is homogeneous function. If f of xy is not a homogeneous function, then this differential equation is not a homogeneous differential equation. For example, dy by dx equals x square minus y square by xy minus x square is an example of a homogeneous differential equation. It's a homogeneous differential equation of degree 0 because this function has degree 0 is how we understand. And let's take another example. This is not a homogeneous differential equation because this is not homogeneous, as highest powers is 1, 1 and this is 0. So they are not with equal powers. Therefore, this is non-homogeneous function. Therefore, given differential equation is not a homogeneous differential equation is how we understand the homogeneous differential equation and a non-homogeneous differential equation connected with the homogeneous function f of x comma y. Now let's see how to solve a homogeneous differential equation as the second method of solving the linear differential equations. The second method is about solving of homogeneous differential equations. So let's see how we can solve using its respective method of solving. Say for example, I take a homogeneous differential equation dy by dx equals y square minus 2xy by x square minus xy. So clearly the right hand side is f of xy, which is a homogeneous differential equation of each degree 2, 1 plus 1, 2, 2 and 2, and therefore this is a homogeneous differential equation of degree 0 on the whole. So let's see how we can solve this homogeneous differential equation. Now In order to solve the homogeneous differential equation, the first step of solving using this method is that I take y equals some v times x, where v is a new variable introduced in the form of y equals vx. That implies differentiating on both sides, I get dy by dx equals d by dx of vx, which is using the formula u dash v, I get v times of d by dx of x plus x times dv by dx using this formula. So we get y is this and dy by dx is this, so that when substituted into equation 1, the whole of y is eliminated and we get the whole of equation gets reduced in terms of v and x. That is, the dependent variable y is eliminated, reduced to v and x. Therefore, substituting in 1, we get dy by dx, which is v plus x dv by dx, that is equal to y squared, which is vx whole square, minus 2xy, which is vx. So substituting in place of y, we get this as x squared minus x times of y, which is vx, is what we get. Now this, on further simplification, gives v plus x dv by dx, and taking v squared common on both sides, taking x squared common on both sides, 2xy v squared minus 2v by taking x squared common here, this is 1 minus v, is how we get by taking common on the numerators and the denominators respectively. So this gets cancelled and this gets reduced as v times of v minus 2 by 1 minus v is what we get on simplification. Therefore, taking this to the right, x dv by dx is equal to v times of v minus 2 by 1 minus v minus v is what we get when we bring plus v to the right. And taking LCM, we get v times of v minus 2 minus v times 1 minus v by 1 minus v. This, on further simplification, gives v times of v minus 2 minus 1 plus v by 1 minus v. This, on further simplification, gives v times 2v minus 3 by 1 minus. So we get this as v times 2v minus 3 by 1 minus v, and therefore continue from here. I have x dv by dx equals v times 2v minus 3 by 1 minus v. So here now we are going to separate this into variables. That is, we are going to use variable separation method, where all v terms are brought to left and x terms to the right. One minus v by v times 2v minus 3 is equal to dx by x is what we get. So taking common here, I get this to be minus of v minus 1 by v times 2v minus 3 is dx by x. Now here we get this separated into variable v on the left hand side and variable x on the right hand side. Now this is clearly using the partial fractions through which we are going to split. So using partial fractions for the left hand side of this of dv is dx by x of dv. So using the partial fractions on the left hand side, this reduces to 1 by 3 times of 1 by v plus minus 3 of dv is dx by x. Now integrating on both sides, we get this to be integral of this is integral of this. So once I integrate this, I get this to be minus 1 by 3, and integral 1 by v dv is log v. And integral of 2v minus 3, 1 by this, is log mod 2v minus 3 by coefficient of v, which is 2. And then on the right hand side, integral of dx by x is log mod x plus c. So eliminating the log, we get the final answer in terms of y by x. Next, further simplifying this, we get this to be minus 1 by 3 of log v plus this can be used as log v root of 2v minus 3 is equal this plus c. So this, on further simplification, taking 3 to the right gives us minus log v root 2v minus 3 minus 3 log x is c. So taking all log terms to the left and taking this on the right, I get log mod v root 2v minus 3 plus 3 log mod x is minus c. Then taking the formula log a plus log b is log ab, and log a power m is m log a, and log a plus log b is log ab are the two basic logarithmic formulae which we are going to use here. So log a plus log b into x cube equals minus c. That implies minus c I can take as log c dash. So eliminating log, we get v root 2v minus 3 of x cube equals some c dash is how we get. Then cubing on both sides, we get the required answer. Continued. Now continued from here, we observe that as we take this to be some constant, I take this as c dash and this reduces to some c. And this integration constant gives us squaring on both sides. I get this as x power c v square of 2v minus 3 equals some c square is how we get when we square on each side. But we know that y is vx, that implies v is y by x. Now we want to retain back the original variables x and y. So therefore, we are going to take v as y by x and substitute in this equation. That implies x power 6 v square is y by x whole square, and 2v, which is y by x minus 3, is c square. So this, on simplification, gives x power 6 y square 2y minus 3x. Now as we see here, this is y by x, so y square by x square times of x, which becomes x cube times this equals c square by taking LCM and multiplying x with x square. This, on further simplification, gives this as a x cube. Therefore we get the final answer as x cube y square 2y minus 3x equals c square. Or this can be adjusted as some constant k, that is x cube y squared 2y minus 3 is equal to some k, because the constant or the arbitrary constant can be replaced for any k in general, and therefore the general solution of the given homogeneous differential equation is x cube y squared times 2y minus 3x equal to k, using the homogeneous method, substitution of y equals vx. Next is the limitations of homogeneous differential equations. Now that every method has its own limitations, let's discuss the limitations of homogeneous differential equation. Now clearly we know that this method is used, or the method 2 is used only when the function is homogeneous. What if the function is non-homogeneous? Is where the limitations are more important. Homogeneous differential equation is solved using y equals vx if and only if the differential equation has a homogeneous function. This it fails if the function is not homogeneous. It fails in solving non-homogeneous differential equations, say for example like x minus y plus 1 by 2x plus 3y plus 4, where in case of these kind of problems I cannot take y equals vx. This method will not help in solving the non-homogeneous differential equations as the case, and hence it is limited only to homogeneous functions where I can solve using y equals vx. Let's see the learning outcome of homogeneous differential equation. As we have clearly seen that homogeneous differential equation indirectly uses variable separation method, as seen in the previous case where we separated the variables x and v's. Therefore, here the learning outcome is that method of solving the homogeneous differential equations uses indirectly the variable separable method is how we understand the separation of variables in using homogeneous differential equations are very much connected. Method 1 and method 2 are connected because method 2 can be used only if method 1 is applied indirectly in the method 2. Now there are two cases through which we solve the non-homogeneous differential equation. In the previous case, we have seen homogeneous differential equation which can be solved using the method starting with y equal to vx. What if the differential equation is not homogeneous? Let's see the method 3, which is solving of non-homogeneous differential equations. Solving of non-homogeneous differential equations has two cases where generally a differential equation in the form dy by dx equals ax plus by plus c by a dash x plus b dash y plus c dash is solved. Clearly this is a non-homogeneous differential equation because the right hand side function is non-homogeneous. The degrees are not same. So solving of this non-homogeneous differential equation has two cases of process, where the first case is if a by a dash is equal to b by b dash, and the second case is if a by a dash is not equal to b by b dash. So with these two cases arising, initially we check for this equal to this or this not equal to this, and hence we differentiate case 1 and case 2. So each of the coefficients of x, y of the numerator and denominator are checked for this, and if suppose this is equal to this, then that implies we take equal to u, or we take this as equal to v. And if suppose this is not equal to this, then we proceed with some other process where we substitute x is x plus h and y is y plus k, where h and k is the point of intersection of these two lines, where hk is the point of intersection of these two lines is how we find. So taking this and this solved, we get the point of intersection of this and this, which is h comma k. The x coordinate is h and the y coordinate of the point of intersection is k. So let's see in brief both the case 1 and case 2 respectively for a non-homogeneous differential equation. Now let's see the solving of non-homogeneous differential equation initially with case 1. So let's take an example problem which involves case 1 of solving the non-homogeneous differential equation. That is, if I have the question which says solve the differential equation dy by dx equals x minus y plus 3 by 2x minus 2y plus 5, then clearly I see that this is in the form ax plus by plus c by a dash x plus b dash y plus c dash. So the given differential equation taken in the form this clearly gives a equals 1, b equals minus 1 and c equals 3, and a dash equals 2, b dash equals minus 2 and c dash equals 5 when compared with the original non-homogeneous differential equation. Now in case 1 we check for a by a dash, which is nothing but 1 by 2, and b by b dash, which is minus 1 by minus 2, which is 1 by 2. Therefore clearly I see that a by a dash equals b by b dash equals 1 by 2. Therefore this comes under case 1. So under case 1 we know that if suppose this equals this, then immediately I take the first part of ax plus by equal to some u. Therefore by case 1 let x minus y equals some u. Then in this case, differentiating on both sides with respect to x, we get 1 minus dy by dx equals du by dx, which on further simplification gives dy by dx equals 1 minus du by dx and x minus y equal to u. So I'm going to substitute this and this in the given differential equation. So let's see what happens when these two are substituted in this differential equation. Therefore, substituting these two equations in the given problem continued, we get dy by dx, which is 1 minus du by dx, equals x minus y plus 3, that is u plus 3, by 2x minus 2y, that is 2 times of x minus y, is 2u plus 5, is what we get. And therefore, clearly I see that this is reduced to a variable separation method where I can separate them into two different variables. So let's see how we can do that. This, on further simplification, gives du by dx equals 1 minus u plus 3 by 2u plus 5. And this, on simplification, gives 2u plus 5 minus u minus 3 by 2u plus 5. That implies du by dx is 2u minus u, which is u plus 2 by 2u plus 5. Then separating into variables, 2u plus 5 by u plus 2 of du equals dx is what we get. Is what we get when we simplify this 2u plus 5, which can be written as 2 times u plus 2 plus 1 by this du equals dx. Continued from here, I can split this using 2 plus 1 by u plus 2 of du equals dx. Now integrating on both sides, I get integral 2 du plus integral 1 plus 1 by u plus 2 du equals integral dx. Then integral 2 times du is 2u plus log mod u plus 2 is x plus c. U, which is nothing but x minus y, x plus c. This x, when brought here, comes as 2x minus x, which is minus 2y, plus log mod x minus y plus 2 equals c when substituted with u. Therefore, the equation or the solution of the given homogeneous, non-homogeneous differential equation is given by the solution as answer x minus 2y plus log mod x minus y plus 2 equals c, where c is an arbitrary constant, using the variable separation method of case 1. So this is the case 1 of solving non-homogeneous differential equation. Now let's solve a non-homogeneous differential equation which involves the case 2 of the method. Now in this case of the third method of solving using case 2, let's take an example problem which involves case 2. For example, I wanted to solve the differential equation dy by dx 2x this 2y plus x plus 1. Then this is clearly a non-homogeneous differential equation in the form ax plus by plus c by a dash x plus b dash y plus c dash. Now rearranging them in the form of x and y, this gets reduced to dy by dx equals 2x plus y plus 3, and x term comes out here as x plus 2y plus 1. Now clearly comparing this with a is 2, b is 1, c is 3, a dash is 1, b dash is 2, c dash is 1. Now to check for a by a dash, which is 2 by 1, which is 2, and b by b dash, which is 1 by 2. Therefore, clearly I see that a by a dash is not equal to b by b dash, because 2 and 1 by 2 are not equal. So this clearly comes under case 2. Therefore, this involves using of case 2. So in case 2, we just take x equals x plus h and y equals y plus k. So using these two, let's see how the given differential equation reduces to capital X and capital Y in terms of x and y substituted there. Therefore, the given differential equation when substituted with x plus h and y plus k reduces to x plus h of this by x plus h plus 1, where the small x is replaced with capital X plus h and small y is replaced with capital Y plus k, where h and k are constants, is how we understand. So expanding through brackets, this comes as 2x plus y plus 2h plus k plus 3, and this is now clearly the left hand side. When x is x plus h, then dx will be d capital X and dy is d capital Y, because differentiating of a constant is 0, so dx is dx, dy is dy. So dy is replaced with dy by dx, which is equal plus 1 is what we get. Now this differential equation is now compared with the case 2 of the non-homogeneous differential equation and its solution. So here h and k is obtained by equating this and this to 0. H and k are found by this equal to 0 by solving the two equations. This equals 0 and this equals 0 is how we set, and h plus 2k plus 1 equals 0 is how we solve these two in order to get h and k. So in every problem of non-homogeneous differential equation with case 2, we reduce the given equation into this form, and then this and this are solved to get the values of h and k. So let's find h and k using the elimination method. This gives us 2h plus k plus 3 equals 0, and multiplying this with 2, 2h plus 4k plus 2 equals 0. Then k minus 4k is minus 3k plus 3 minus 2 is 1. That implies k is 1 over 3. And when k is 1 over 3, we find the value of h. When substituted gives h plus this, when substituted in this, gives us h equals 2 by 3 plus 1, 5 by 3, which is negative 5 by 3. Is what we get. Therefore, the two values of h and k are h is minus 5 by 3 and k is 1 by 3 is what we get. Therefore, my x is x plus h and y is y plus k. Using this, I get h is minus 5 by 3 and k is 1 by 3, which I substitute in this after solving the entire differential equation. So with these values of h and k, this differential equation reduces directly to this 2x plus y by x plus 2y. With these two being equal to 0, they get eliminated. Continued. Therefore, by substituting h and k in the transformed equation, we get dy by dx as 2x plus y is x plus 2y is what we get. Now this is clearly, as seen, is homogeneous differential equation in x and y of degree 0. So clearly this is a homogeneous differential equation in x and y of degree 0. Therefore, by using the second method of solving the homogeneous differential equation, we take y equals vx and then differentiate both sides with respect to x. Differentiating both sides with respect to x, we get dy by dx equals v plus x dv by dx using the product rule of the differentiation. So substituting in equation 1, we get v plus x dv by dx equals 2x plus y, which is vx, and x plus 2 times of y, which is v of x, is how we get. Then simplified. Then this, on taking x common and simplified, we get 2 plus v by 1 plus 2v, which needs to be eliminated using the separation method.